In the last video, we talked about different strategies that you can use to analyze a circuit and calculate the properties of voltage, current, and resistance for each component in that circuit. In this video, we're going to look at one specific design of a circuit known as a potential divider, and the applications that that holds are going to be really useful to us in designing a circuit to accomplish a task. To do this, first we need to go back and review some different types of resistors that exist. When we looked at these symbols before, we basically just said all of these boxes here, they're different types of resistors. Now, let's dig in and figure out what these are actually going to do and why they might be useful to us. This very simple resistor, the one that we've been using so far, this is what it actually looks like in real life. It's this little cylindrically shaped thing, and it's got these colorful bands on it. Those bands are actually a code to designate what resistance it is. You can read the nomenclature and look on a table to figure out, based on what colored bands it has, what resistance it provides. If you just split one of these open and look inside it, it looks something like this. That something with a very low resistance up here can change to something that's a very high resistance by changing that inner structure. Notice what's going on here is it's basically like a coil of wire. And as we saw before, wire can have resistance. We calculated the resistance of a wire using this equation. Resistivity times the length divided by the cross-sectional area. Well, as we go down these three, notice that the length has to get longer because we are winding it more and more times around that cylinder. And by doing that, we're also making the cross-sectional area smaller. So it has more length and less area, which results both of those giving it more resistance. So the longer the coil and the thinner the wire provides more and more resistance. So in the same form factor, these are actually different resistances. Another type of resistor that we're going to use an awful lot is something known as a light-dependent resistor. The symbol here looks like this. It looks just like the resistor with a couple light rays incident on it. Now, it looks something like this here in real life. You have probably seen these in a nightlight. That this little button-looking thing, that's actually a light-dependent resistor that's sensing the brightness of the environment and adjusting its resistance accordingly, and in that circuit then turns on the light when the lights go out. Now, the relationship here between the light and the brightness is an inverse relationship. So if it's really bright outside, bright incident on this resistor, it ends up having a lower resistance. So it's low resistance when it's bright outside, and then vice versa. If it's dark, if it's very dim, it ends up having a high resistance. So it changes opposite to the light. If we look at something called a thermistor here, it has a very similar sort of situation. It's an inverse relationship. This is what it looks like here. You probably have a thermistor in like a digital thermometer. It's a way of easily measuring what the temperature is because the resistance changes according to the temperature. That if you have high heat, the hotter it is, the smaller the resistance is on this thermistor, and since it's inverse, vice versa. So lower the heat, the higher the resistance. Now, another type of resistor that we're going to see is something called a variable resistor. Another form of that is a potentiometer. And what that looks like is something like this. This is a potentiometer. That it's basically just a big coil of wire here wrapped around this cylinder. And there's this slider here that you can stop the coil wherever you want. So basically, it allows you to choose the length of wire that you want to use. And remember, the longer the wire, the more resistance it has. So the more of this coil you allow, the more resistance this potentiometer is providing. Now, if we shrink that down, there's another way of doing a similar thing in a variable resistor. This is your classic like dimmer switch that if you rotate it, in this case, you are changing the amount of resistance. That's also used in dials on like a soundboard. They're just variable resistors. Here's an example that's a slider that as you're sliding, you're changing the resistance just by sliding it up and down. So you might have a dimmer switch that looks like one of these two designs in your house. Well, these can be used in a circuit design that we call a potential divider. We saw this in the last video, talking about the potential difference that the battery provides, and then dropping down at each resistor that it hits along the way. And each resistor, we said, had a voltage drop. Well, if we set up a circuit like this, the total voltage supplied is divided across these different resistors. That potential is divided, the potential divider. So what we're going to do here in this potential divider is we'll design it so that the drop is the amount that we want for each given resistor. So your design ultimately looks something like this. It allows a circuit designer to tune the voltage that's being delivered to the desired components. And the way we do that is we basically pull the voltage, or we measure the voltage across one of our resistors. So here we're looking just at resistor 1, R1, and measuring what that output voltage would be across it. So it's essentially the same thing as taking a voltmeter and just seeing, okay, what is the voltage of R1? And how we change R1 and R2 respectively to each other will change the amount of voltage that this outputs. It will never be bigger than the voltage supplied by the battery or the power supply, but we can have a larger piece of that pie depending on how these two relate to each other. So let's look at an example here. I've got two resistors, and now I'm increasing this resistor that the voltmeter is measuring. If I increase that resistance, you'll notice that the voltage is changing as I change this resistor's value. I'm going to start out here, both of these 10. So this 10 volts splits into 5 volts each. But as I increase this voltage, increase the resistor, I'm increasing the voltage. So as R1 goes up, V out goes up, the voltage. If I decrease this, I am decreasing the voltage. So as R1 goes down, V out goes down. Basically, if this resistor is bigger than this resistor here, the other one, it's going to take more of the total, like more than half of that total, because it's more than half of the overall resistance. If it is less than that resistor, it's going to take less than half of the voltage because it's less than half of the overall resistance. If instead I design this so that I am changing R2, now I can look at this. Increasing R2 actually changes the voltage across this other resistor. That even though this is staying 10 ohms, its proportionality to the total resistance that's there is changing. So if both of these are 10, this is still 5. But if this starts to get bigger, then this 10 ohms is a smaller piece of the pie, so the voltage goes down. If R2 goes up, V out across R1 goes down. If R2 goes down, this voltage becomes bigger, so V out goes up. Now, those might be useful to just rewatch a couple times just to see how that relationship holds true. But here is all of that together in one place. That R1, if you increase that or decrease that, that will control your voltage out or voltage across R1 directly. R2, if you're changing that one, it basically has an indirect effect on this output voltage because it's making R1 bigger or smaller part of the overall resistance accordingly. I think it's sometimes easier just to see what this looks like in action. If I have a voltage or a potential divider set up like this, where R1 is 30 ohms, R2 is 220 ohms, and the voltage is 10 volts, I'm going to measure this voltage out here across R1. I want to figure out what that output voltage is. So this is what I'm looking for. I'm looking for the voltage of R1. Now, that's really the only thing that this is doing for me. So I'm just going to ignore that was there and just set my sights on finding R1, or on V for R1. Notice now that this is a very simple circuit, that a potential divider is just really two resistors in series with each other. And if they're in series, to figure out the total resistance, I just have to add them up. 220 plus 30 is 250 ohms. If I know the total resistance and I know the total voltage, I can find the current using Ohm's law. Ohm's law says that the current is equal to the voltage divided by the resistance. 250 divided by 10. That is flipped around. Let me change that right now. There we go. 10 divided by 250 will give you 0.04 amps. So that is my current flowing out of the battery. But since this is a series circuit, that current is the same for every resistor. It does not split. Even when I had that V out in there, that was just measuring the voltage across it. It doesn't actually flow through that. That has a very high resistance, and all of it stays in the circuit. So this 0.04 amps goes all the way up. That's each resistor's current as well. And remember, what I was trying to solve for here was this voltage out, this voltage across R1. Now I know I and I know R. I can calculate the voltage across R1 using Ohm's law. I times R, the current times the resistance, is 0.04 times 30, or 1.2 volts of voltage being measured across this R1. One thing I want to point out here is that this is smaller than this, and it's less than half of the overall. So 1.2 volts is a small part of that 10 volts, and that kind of makes sense because 30 ohms is a small part of the total resistance since R2 was 220. So that's a good check in the end that the smaller voltage goes with the smaller resistor. If I wanted, I could find R2 as well. It would turn out to be 8.8 because that has to add up to the 10 volts going around in that voltage loop. So before we get into some real life examples, starting out with a light dependent resistance or LDR, I just want to remind you of how this works. So it's designed to perform a function when the amount of light changes. So here's a night light that I actually have in my daughter's room. Notice this light dependent resistor on the top. If I cover it with my finger, I can turn the night light on. I can also turn it on, of course, if I turn off the lights. That turning off the lights or dimming that resistor turns the light on. That's the way that that circuit is designed. Here's another really amazing example using a light dependent resistor. This person, I did not do this. This person hacked it up. So there is a light dependent resistor controlling this little servo motor that looks for these obstacles. If the light dims, it causes the servo motor to push the space bar. So the little dinosaur jumps, and it just works out to be the exact right time because they placed this light dependent resistor at the position it needed to be so that when it triggers the jump will be successful. Just amazing. So let's look at a very specific example here. This problem solving process is one of the more challenging ones that we'll see. So let's take our time and look through what we've got. A light dependent resistor, LDR, has a resistance of 8 ohms in bright light and 140 ohms in low light. So as a reminder, it's an inverse relationship. So the brighter it is, the smaller the resistance. An electronic switch will turn on a light when its potential difference is above 7 volts. What should the value of R2 be? So let's start with figuring out what we want to find. We're trying to design the circuit to figure out what R2 has to be. The value of R2 would be the resistance of R2. That's what we're looking for here. Now let's go back and figure out what we've got. We know that our voltage, our battery here, is 9 volt battery. So our total voltage in the circuit is 9 volts. We also know that we are looking at an electronic switch that only works if it is above 7 volts. So this switch is going to measure 7 volts. And now that is basically measuring the voltage across R1 here. So I'm going to say that R1 is 7 volts. That's essentially how I would set that up if it was a voltmeter instead. Then I can just ignore that electronic switch. All that's really doing for us is telling us which resistor we're measuring the voltage across, and it has to be 7 volts. All right, now let's look at this light dependent resistor. I know that it's 8 ohms in bright light and 140 ohms in low light. And I'm trying to figure out when to turn the electronic switch on to turn on this night light. Well, a night light should be on in low light. That's kind of the goal of it. So I want to use the resistance that matches the condition for when we want this switch to turn on. and that is low light, 140 ohms. So I can plug that in here. R1 has to be 140 ohms. I can plug that in here. R1 has to have a resistance of 140. Now, there's a couple steps that I need to do in order to get here. First, if I know two of the three, really in any of these rows or columns, I can always find the third. Here, if I want to find the current through R1, all I have to do is use Ohm's law. Ohm's law states that the voltage divided by the resistance will find the current. 7 divided by 140 is 0.05 amps. Next, the current is the same throughout the circuit. There is no branch here. It's just two resistors in series with each other. So this 0.05 is the same for R2. It's also the same coming out of the battery. There is no separate branch or a junction here. Next, I can use a voltage loop to figure out what the voltage across R2 has to be. This loop here says that the voltage provided has to equal the voltage dissipated. I already figured out that R1 had to be 7 volts because that's what the electronic switch was measuring. So the total 9 volts, 7 already gets used by R1. So that means that R2 has to have 2 volts being used. It's kind of like looking at that waterfall that each one uses part of that 9 volts. Well, 7 was already used, so the only thing remaining is 2 volts. Now all I need to do is then, again, that's where the electronic switch is, to calculate the resistance of R2. Resistance is just voltage divided by current. So that ends up being 40 ohms. I could also find the total resistance. Here I could solve it a couple different ways. I could say 9 volts divided by 0.05 to figure out that would end up being 180. Or I can add these together and find 180 that way as well. Let's look at another example here. Instead, using a thermistor. So you'll notice that this thermistor is in the R2 location. That's the symbol for a thermistor, a resistor that changes with temperature. This thermistor has a resistance of 0.25 when it's in the heat of a fire, and a resistance of 650 when it's at room temperature. Again, an inverse relationship. The hotter it is, the smaller the resistance. An electronic switch will turn on a sprinkler system when its potential difference is above 6 volts. What should the value of R1 be? All right, again, let's start with what we're looking for. Value of R1, we're trying to find the resistance of R1. Now, the things that were provided here, we know that the voltage of the battery is 9 volts. We know that this electronic switch works when the potential difference over R1, the way it's designed here, is 6 volts. All right, that's enough to tell me that R1 has to be 6 volts. So this can go away. I don't need that anymore. Now, I want to look at this resistor. The sprinkler should turn on if it's hot. So I want to use the resistance when it's in the heat of a fire. That is 2.5 ohms. So the resistance of my thermistor, this R2, is 2.5 ohms here. Now there are a few things I need to do to get all the way to R for R1. First, I can use a voltage loop to figure out the voltage across R2. Any time I am missing 1, here I can always find the missing one in a column or a row. So here I know that 9 volts is supplied. R1 dissipates 6 volts of that because of the electronic switch measuring 6 volts. So the only thing left now is 3 volts. Next, I can calculate the current through R2. Current is just voltage divided by resistance. 3 divided by 2.5 is 1.2 amps. Since this is one pathway, the current is the same throughout the circuit. So this 1.2 amps is the same for R1, and it's the same total coming out of the battery, which means that I have everything except for the resistance for R1. 6 volts divided by 1.2 amps will give me a resistance of not 7.2, but 5 ohms of resistance there required to make this work the way expected. Again, the goal here is to basically get this electronic switch above that 6 volt threshold for the sprinkler to turn on. The only way to do that is if this is kind of fixed at 2.5 ohms, to make this bigger, to make it bigger than that 2.5 ohms, so that it is a large enough part of the overall resistance so that it takes 2/3 of the voltage, 6 volts of the 9, which means that it's 2/3 of the overall resistance. All right, those two examples are pretty challenging. It might be worth going back and rewatching them. You should be able to identify different circuit diagram symbols for these different types of resistors and describe how these changes, like light and heat, can change a light-dependent resistor and a thermistor. Describe how changing the resistor affects the voltage drop, and then design a potential divider circuit to perform a certain task. Note that the LDR and the light-dependent resistor and the thermistor are both in different locations, because that's what was required for that potential difference to rise high enough across the switch that was turning on the light or the sprinkler system.